Today we are going to discuss power and energy in CMOS logic. That's what we're going to discuss. So, as you guys have probably experienced in your own lifetimes, that we have more complex cell phones today, more complex computers. They do a lot more than than the cell phones or computers used to be even 15 years back. But one of the things that has happened as a result of this is we have gotten higher performance, higher functionality, but we have also increased the total amount of power dissipation in most of these electronic devices. So it is very important for us today to understand the sources of power dissipation in CMOS logic, and also understand what are the mechanisms for controlling some of these aspects of power dissipation, and also minimize the amount of power dissipation for let's say the same quality of performance, the same quality of user experience. Reducing power dissipation eventually leads to designs which are, for example, in the case of mobile devices, the battery would last longer. So that's, definitely an advantage. In terms of, let's say, laptops or desktops and other, mainframe computers, reducing the power dissipation, reducing the cost of power dissipation is also very important because it reduces the operating cost of these devices. The utility utility bills are lower. It's also better for the environment. So there is a huge push from the industry today, as well as from research and academia, to understand the limits of power dissipation, how low can power dissipation be in CMOS logic, and what are the mechanisms for achieving that. And you can also understand that higher power dissipation leads to higher temperature. So many a times, particularly in the case of mobile devices, you cannot make the device very hot, otherwise you would not be able to use it like on your palm. So that's the motivation for us to kind of look at power dissipation. And power dissipation, one of the things I can say is power dissipation and challenges in power management have worsened with technology scaling. So there are multiple reasons why power is dissipated in CMOS logic, and if I have to look at the total power dissipated, let's say, then I can split it up into two components. The first one would be dynamic power, and the second one would be what is called static power. And very simply put, a dynamic power dissipation or dynamic power is consumed when the circuit is switching. The static power is consumed when the circuit is not switching. Right? So that's called static power. And we will look at why static power is important as well, particularly in mobile form factors. The dynamic power, which is the power which is dissipated during switching activity, can again be divided into two main components. The first component is what is called switching power, and the second component is called short circuit power. In the earlier days of CMOS logic, switching power was the most important component of power dissipation, and still today is the most important component of power dissipation. But with technology scaling, particularly short circuit power has also gotten worse, and static power has gotten exponentially worse. So that's why we have to also keep track of these two components of power dissipation when we discuss, when we discuss total power dissipation in the case of CMOS logic. It is also important for you guys to make sure that you have a clear understanding of the difference between power and energy, right? Power and energy. I'm sure you know, but make sure that you don't forget that, because we are going to look at power and energy interchangeably and see how we can translate from one to another. So again, energy, so let's say power is the rate of change of energy. So we know that. We'll come back to this later. So this is all the background that we need, and we will start looking at each and every component of power dissipation, starting from dynamic power, and particularly starting with the switching component of power dissipation. So, switching dynamic power. So let me make it a little smaller. So we are going to start with dynamic power dissipation, and we are going to look at the switching component of that. So switching. So here we will start looking at switching energy. And from energy, we'll go to power. So let's look at switching energy. So far in this course, and later on, we will, those of you who are going to take 4130 later, we have, more detailed discussions of power dissipation, and we talk about the aspects of scaling and why, it has gotten worse with technology scaling. But in this course, we are going to give you an introduction to power dissipation and the main equations that connect power dissipation with the various design parameters. We're going to look at that. But one of the things that you have seen in this course and any other VLSI course that you will take, that we always use this inverter as a prototypical device, like a prototypical logic gate. And if you can analyze an inverter, we can take the same analysis and apply it to other kinds of logic gates as well without a significant change. So the basic understanding can come from an inverter, and any other logic gate that you study or discuss would be like an extension of the inverter characteristics. So even for dynamic power, and to understand the switching energy component of dynamic power, let us look at an inverter. So let's say I have a PMOS on the top and of course an NMOS on the bottom, and let's say the inverter is switching. And from the discussions on delay, you have seen that whenever I have an inverter or any logic gate, I can assume without any loss of generalization that there is going to be some sort of a capacitor at the output, right? So this is, let's call this CL, or the load capacitor. And the CL, the load capacitor, will typically be a combination of the output capacitance from this inverter itself. There can be some wire capacitance that comes from the interconnects, and it can have also some gate capacitance of the load circuits, right? Some gate capacitance or input capacitance. I can also call this, C input. Let's call this C input from the load circuits, whatever fan out I have. So let's lump all of that capacitance into one value of capacitance that I'm calling CL at the moment. Let us assume now that this is the input and this is the V out and this is VDD, right? And assume that the input is now switching. So the input switches from, let's say, 1 to 0, right? So the input switches from 1 to 0, which means during this transition, so this is one switching transition, and then there is another switching transition when it goes back from 0 to 1 back up. So this is the second switching transition. So this is, let's call this switching transition number 1, and let me use another color, and let me call this switching transition number 2, right? So during switching transition number 1, what happens is that this PMOS is going to charge up this output capacitance, and the output voltage will start rising. So this is V in. So if I look at V out, so you have seen that this charging is going to be exponential. So it will slowly charge up. So it was initially 0, it charges up, and then during the following transition, it will start discharging again. It will discharge back, and the discharging will happen through the NMOS. So the PMOS is responsible for this portion of the charging, and the NMOS will be responsible for the discharging process, where this capacitor will get discharged out to ground. So every clock cycle, which means when I go when I have a full period, which means the signal goes from 1 to 0 back to 1 for this entire clock cycle period, I can see that there would be one charging event and one discharging event, and there will be an energy dissipation component associated with each of these switching activities in 1 as well as in 2. So our job will be to find out what is the total energy dissipated during charging and what is the total energy dissipated during discharging. So the first thing that I'm going to do is look at the process 1, where we are going to find out an expression for the charging energy, like how much energy is dissipated, what happens to the energy stored, and so on. So we are going to look at the various components of charging energy. So the first thing that we want to do is we want to understand that energy. What is the energy drawn from the supply? So so that's what I'm interested in, which is called VDD. So the supply is VDD. So the first thing that to realize is whenever I have, let's say, some node in a circuit, and let's say the voltage here is V, and there is current, there is current flowing into this node with potential V, then the power associated with this is Vt dot IT, right? So the voltage multiplied by current. So if there is current flowing into this node, and if there is voltage at this node Vt, so then the instantaneous power is going to be Pt is Vt dot IT, right? So if you look at, so I'm trying to find out what is the energy drawn from the supply, which is VDD. So the first thing that I want to do is, before I go to energy, let's look at the power drawn from VDD. So the power drawn from VDD must be PT. So let's call it P VDD T is the voltage, and the voltage in the case of VDD is constant, so that's VDD, multiplied by IT, where IT is the charging current. Right? So this is total amount of current that flows from the VDD to the output capacitance CL. So the question is, what is that charging current, right? So if you look at the charging current, the current IT, which is the charging current, flows from VDD through the PMOS and charges CL, right? So it's the same current. So if you look at some sort of an abstracted view, so what we are doing is, this is the RP, and this is the CL, and this is the current that flows in, right? So this is the I charging. This is the charging current. So I can write an expression for the charging current, which is the current that is drawn directly from VDD. So I charging, function of time. It's simply VDD. So not VDD. So the current. So if this is V out, we can say that this is TL ddt of V out, right? So we can say that. So that's the total current if CL is constant. So for a constant capacitance, we can assume that the total current that is flowing in, so this is the same current that flows into the capacitor, is the same charging current. That's essentially CL multiplied by ddt of V out. If CL is not a constant, the more generic expression should be I charging, function of time, should be ddt of the charge on the capacitor, which is ddt of CL V out. And if this is constant, if CL is a constant, then it becomes CL ddt of V out. So that's the total charging current. So let's go back to the power now. So what is P? The power drawn from VDD. That becomes VDD multiplied by CL multiplied by ddt of V out. And again, I'm assuming that the output capacitance is constant, so that this expression becomes CL V out, CL ddt of V out. So this is the total power, the power which is drawn from the supply. So what's the energy drawn from the supply? So let's call it E VDD, the energy drawn from the supply. So that would be integration of power from time equals 0 to infinity, right? So the total time it takes to switch. And this becomes VDD times CL times ddt of V out dot dt, right? Now, in order to perform this integration, I need to perform the integration from time 0 to infinity. But as opposed to doing that, I can also make a small transformation. I know that at time t equals 0, right? I start with the fact that the output voltage V out is simply 0, and when time goes to infinity, the output voltage V out goes to VDD. Right, so it's a complete charging process. So in the charging process, it takes a very long time. Even if it takes a very long time, eventually I will get to VDD. So the voltage swing on the output goes from 0 to VDD. So that allows me to change this integral from time to V out. So I can now rewrite VDD, energy VDD, as simply VDD CL, and this becomes d V out, and this goes from V out of 0 to V out of VDD. Right? So simple transformation where we transform the integral on time to an integral on voltage. So what is this? So this simply becomes now VDD, CL, which are all constants, multiplied by V out, and V out goes from 0 to VDD. So this is the final result. So this becomes CL VDD squared. So this is the total amount of energy that I have drawn in from the supply when the output capacitance got charged. So in summary, I can write during a 0 to 1 transition at the output, CL VDD squared energy is drawn from the supply. So I draw this kind of energy from the supply. I'm going to draw C VDD squared of energy from the supply. So if I now go back to my, to the transition, so if we remember, so we looked at V in goes from 0 to 1. So this is the transition I'm looking for. And the V out goes from, so this goes from 1 to 0, the V out goes from 0 to 1. So during this transition, right, so both of these, this is the same thing. So during this transition, the energy drawn from VDD is CL VDD squared. So that's what we saw. So the question is, where does this energy go, right? So this energy is, if you go back and if you look at the circuit, it's essentially, a charging process where you are charging up the output capacitance CL. So since there is a capacitance involved, and from, I'm sure from, previous courses like 2040 and all, you guys know that, when you have a capacitor, you charge up the capacitor can store energy, right? It's one of those, reactive elements. It's an energy storage element. So it will be able to store energy whenever you charge up the capacitor. So definitely a part of this energy that we have drawn from the supply will go in charging up the capacitance and storing energy in the capacitance. So that's the next thing I'm going to try and estimate. So what I'm going to do is I'm going to try and estimate what is the energy stored in CL after a complete 0 to 1 transition. And when I say a 0 to 1 transition, I mean the 0 to 1 transition on the output. So the energy on the capacitance, again, we are looking at the capacitance now, right? So again, if you look at the circuit, this is RP, and now this is, this node is V out, and this is CL. So I'm interested in the energy in this capacitance. So the energy in the capacitance, okay, let's start with the power. That's easier. So we'll start with the power on the capacitance. So that should be the total current. So the current that is going into this, the charging current that is going into this, into the capacitance, multiplied by, in the previous case it was VDD because I was looking at the energy drawn from the supply, but now I'm interested in the energy in the capacitance. So the voltage here, the relevant voltage here is the V out, because that's the node that's providing the current to the capacitance. So this must become V out, which is also a function of time. It is slowly charging up. So the expression for PC, the power which is going into the capacitance, should be the current multiplied by the voltage across the capacitance. And again, assuming that the capacitance CL is constant, I can write I charging as a function of time is CL dV out dt. So you can see that the equation becomes a little different from what we did last time in case of energy drawn from the supply. So PC as a function of time, the power into the capacitance now becomes CL V out dV out dt, right? So in the previous case, it was CL VDD dV out dt. Now it's CL V out dV out dt, all right? So let me see if there are any questions on Blue Jeans. Okay, I don't see anything. Okay, so if you guys have any questions, just write on the chat window, and I'm going to address that, periodically. So this is the power which is drawn into the capacitance. Now the question is, what is the energy corresponding to that? So how much energy do I consume in charging the capacitance? So EC during this charging process will be integration again from time 0 to infinity PCT dt, which very similarly will now become time 0 to infinity CL V out dV out dt. Again, same reasoning. I'm going to transform this into an integral on voltage. So V out goes from 0 to VDD. This becomes CL V out dV out. And if you integrate this, what do you get? So you get CL. This is V out squared over 2 going from 0 to VDD. So this will lead to half CL VDD squared. And this is something that you probably can identify very easily from previous classes, analog classes or 2040, where the total energy stored in a capacitance when it is charged to a voltage of VDD or any V will be half CV squared, right? So we know that. So, and that is the same result we have again deduced in the context of switching a capacitance at the output of an inverter. Same thing, right? So what we have seen here is that during charging, half CL VDD squared of energy is stored on the output capacitance. So the thing is, so every time I go from 0 to 1 at the output, I have drawn in CV squared of energy. So that's what we saw. So CV squared of energy. And out of the CV squared of energy, half of that, which is half CV squared, gets stored on the output capacitance. So I have to still account for the rest of the energy, right? So the rest of the energy, which is C VDD squared minus half CL VDD squared, which is the same as half CL VDD squared. So this is still unaccounted for. And this is the energy which is dissipated across the resistance Rp during charging. Okay, so we know that whenever current flows through a resistor, let's say there is a current I flowing through a resistor R, the power corresponding to that is I square R, right? So whenever so there is a power dissipation corresponding to a flow of current through a resistor, which is I square R. So the same thing is happening here as well. So the current through the resistor, so there is a current that is flowing through the resistor, and whenever the current flows through the resistor, there will be a power dissipation associated with that. The power will get essentially transformed into heat. So the resistance will heat up, and that's why the temperature of the device will increase. So the PMOS will become hotter. Okay, and as that happens, we end up with some power loss, so loss in the process. And that, if you integrate that over the entire charging period, from very simple algebra, we see that that should be half CV square, and half CV square of energy is kind of lost in the process of charging. So this is a very interesting result that we see, that in order to charge up an output capacitance, we so the total energy stored at the output capacitance during a 0 to 1 transition is half CV squared. Energy dissipated across Rp during 0 to 1 transition is another half CV squared. And the total energy drawn from VDD to charge CL, that's the sum of these two, right? So half of it is stored in this capacitor, half of it is lost. So the total is CL VDD squared. And we have essentially started from this, and we showed that it is indeed CL VDD squared. And we saw that the energy stored in the capacitance is half of that. So the rest of it must be dissipated across the resistance. So this is the portion of energy which is lost as heat. And when you run a computer, or you are using your mobile phone, you know that it feels hot to touch, and that's because of this, because there is a lot of inverters and NAND gates and NOR gates and all kinds of gates which are constantly switching. And every time you are drawing in current from VDD, from the supply, and charging up capacitors, the capacitor itself is not lossy, right? It will store energy. It is not going to dissipate energy. But the process of charging a capacitance will actually dissipate an equal amount of energy on the resistance, which is the Rp, and that would translate into that there will be an energy transformation. The electrical energy will become heat energy, and the temperature of the chip or the microchip will increase, and as a result, your whole phone or whatever mobile device you have will get hotter and hotter. All right. So there is one more important observation that you should be aware of, and that is the energy dissipated across Rp, which is half CLV square, is independent of the value of Rp, which is a very unique and interesting result, right? Because once we did all these deductions, we saw that the energy dissipated is just half CV squared. It does not actually depend on Rp. What does it mean? It means that, so even if we use a wide transistor, a wide PMOS transistor, PMOS device, so that Rp is low, the total energy dissipated will still be half CVDD squared. It is not going to change. So even if you make the PMOS, more conductive, as in you increase the width of the PMOS and you draw on a lot of current, the delay of the circuit will change, right? The delay, however, so the charging delay, however, will decrease, right? So the charging delay, of course, decreases, the inverter becomes faster, but the total energy dissipated in the process does not change. So that's a very unique result. So it really doesn't matter how conductive your channel is, or if you go from like a silicon MOSFET to some exotic transistor material which gives you much lower resistance. Yes, you can make things faster, but you are not going to fundamentally change the amount of energy dissipated in the charging process. And that's a very unique and kind of a boundary condition that you cannot do in CMOS logic. You cannot do better than that, because this is very fundamental to the process of energy dissipation. So what we have seen so far is the charging process where there was Rp, and then there was this 0 to 1 transition at the output, and during the 0 to 1 transition, I lost half CL VDD squared here on the resistance. I drew CL VDD squared from the sub, and I stored half CL VDD squared on the capacitance. After that, the input voltage is now going to go back from 0 to 1. So this was this transition, right? 1. And now it is going back from 0 to 1, the opposite transition. And during this, so this is number 1. So in the second phase, where the input switches from 0 to 1, of course, the NMOS will now play a big role. The NMOS turns on. And this capacitance, the output capacitance that I had, CL, which was storing charge, which was VDD at this point at the beginning of the discharging process, will now start to discharge, and this VDD will slowly discharge to this resistance Rn, and the charge will be lost to ground. So the output voltage V out will now make a transition from VDD all the way up to 0 in the discharging process, which is a 1 to 0 transition at the output. So that's what's going to happen in the discharging process. So this is the discharging process. So the total amount of energy, so at the beginning of the discharging process, the energy stored on CL is half CL VDD squared. After a 1 to 0 transition, V out at the output voltage, the total stored energy on CL goes to 0, because it is completely discharged. So the final energy stored on the capacitance is 0. So the total amount of energy which is taken out from the capacitance is half CL VDD squared, right? So that was the original energy in the capacitance. Final energy is 0. So the total amount of energy taken out from the capacitance is half of CL VDD squared, which essentially it means that half VDD squared energy is dissipated across the NMOS during the discharging process. All right. So that's that's the symmetry of the system. So during the charging process, the total amount of energy drawn in from the supply is CLVDD squared. During that time, half of that gets dissipated across the PMOS. We lose that energy. Half of it gets stored on the capacitance. During the discharging process, that half of the half CLVDD squared, which was stored on the capacitance, is discharged through the NMOS, and the energy is dissipated across the NMOS, and we lose that energy. Again, during the discharging process, we see, one of the things you can see is during the discharging process, we just have the NMOS connected to ground, and then there is, capacitance which is discharging. So during discharging, the circuit is disconnected VDD, right? So there is no connection to VDD. As a result, I'm not going to draw in any more power or any more energy from the VDD. I cannot draw in any more energy from the VDD because I'm already disconnected from VDD. All the activity that's going on is at the output voltage V out, and that's getting discharged through the resistance Rn. Again, just like the case of the PMOS charging the capacitance, here as well, here the total dissipated energy during discharging is also independent of Rm. Okay, so you can make the NMOS device as wide as you can. It will improve performance, but it will do nothing to the energy dissipation. The energy dissipation component of the switching energy. It'll still dissipate a full, half CVDD squared. So the total energy dissipated by an inverter when the output goes from 0 to 1, this is half CLVDD squared. So I'm talking about the dissipated energy. And then again going from 1 to 0, that's half CVDD squared. So when you add these two up, so the total energy dissipated is CLVDD squared, which is the same amount of energy that you actually drew from the original supply at the beginning of this clock cycle, at the beginning of the cycle. So whatever energy you are drawing in from the supply eventually has to get lost. So every cycle, like a full cycle, what we end up happening is that the total switching energy, just switching, let's say, per clock cycle is CLVDD squared. Half of it is lost during charging and half of it is lost during discharging. All right. So this is the energy for switching, energy during switching over a full cycle, and this is energy. Remember, this is energy. We are calculating energy so far. We haven't talked about power. We'll do that later. But this is all about energy. All right. All right. Let me see if there are any questions. Is it all making sense so far? All right. So since you guys are not responding, I'm going to assume that it's making sense. So if this is this is the first component of dynamic energy, and this is of course a part of dynamic energy because, as if you go back to my first slide, this is happening because of charging and discharging. So this is when the circuit is actually switching, right? So I care about the dynamic component of energy. So this is the switching energy or the switching energy part. We'll come back to the power later. Let's now look at the short circuit component as well of switching. So when an inverter switches, what happens? Why is there a short circuit? What is the short circuit that we see, and why does it happen? So I'm going to talk about the second component, which is short circuit energy. Right. So what is short circuit energy? So we talk about this PMOS and the NMOS of an inverter, in this fashion, and we know that the input when the input makes a transition from, let's say, 0 to 1, or it goes from the input makes a transition from 1 to 0 and back to 0 to 1, there is charging of this capacitance, there is current that flows during the charging process. But you also know that when the input makes a transition, if you remember the voltage transfer characteristics of the inverter, whenever an inverter switches, when the input switches, the inverter VTC looks like this, right? So when you switch the input from 0 to 1 and back to 0, there is a portion of the voltage transfer characteristics where in this region, right, when the input is, let's say, in this region, when the input is somewhere here, both the NMOS and the PMOS devices are on at the same time. This may happen for a very short duration of time, but even if it's a very short duration of time, there would be a small sliver of a time when both this PMOS device and the NMOS device are on. As a matter of fact, they are both in saturation. And that's when there would be a direct path from VDD to ground for current to flow. Of course, a part of the current, a large portion of the current will go and charge up the capacitance. But during this signal transition period, there will also be this sliver of a time when both the PMOS and the NMOS will be on, and there will be like short circuit from VDD to ground, and there will be a direct short circuit current that is dissipated from the VDD to ground. So in previous let's say logic design classes like 2020 and all that, we always assume that when the PMOS is on, the NMOS is off, and vice versa, which is always true in the steady state. But during the switching event, when the input is making a transition and correspondingly the output is also making a transition, during a switching event, there is this very short duration of time. Both the NMOS and the PMOS would be simultaneously on, and that would lead to short circuit current, and the short circuit current will be associated with a short circuit energy dissipation during the switching event. So if I have to write it down in words, what I can say is during signal transitions, this doesn't matter whether I am transitioning from 0 to 1 or 1 to 0. So, so this is like both 0 to 1 and 1 to 0 transitions. PMOS and NMOS both simultaneously on, and contributes to short circuit current, and because of the direct flow of current, there is also energy dissipation. So if you visualize this, so if you look at the input, right? So let's say the input makes a transition. You have already seen what rise times and fall times are. Let us assume that the input looks like this, right? So it is not like a vertical jump from 0 to VDD and a vertical fall. There is a finite non-zero rise time and fall time for input signals, and correspondingly the output will also have a transition time, right? So it goes from like this, slowly starts transitioning, and let's say it takes time, then again it slowly starts transitioning, goes up, right? So there is a transition time associated with it. So during this transition time, which we are going to call now, let's say, the rise time and the fall time of the input. So the input is what will dictate the short circuit. So this is the rise time TR, and this is the fall time TF. During this period, if I now look at the current, right, the total current, the short circuit portion of the current, SC, this portion of current, what we can say is initially when the input is 0, then of course the NMOS is off. There is no short circuit current. Then during this signal transition, both the transistors are slowly turning on, so the short circuit current keeps on increasing, increases to the maximum value somewhere in the middle, then it starts falling off, and then it goes back to 0. Once the output has become 1, then the PMOS becomes off, and there is no short circuit current anymore, and the current goes down to almost 0. And then it continues to be 0, 0, 0 all the way till it faces another switching event. In the next switching event, when the input goes from 1 to 0, again the short circuit current starts increasing because both the transistors are slowly turning on. It reaches a maximum somewhere in the middle, and then it comes down again slowly, and then it goes back to 0. So this is the profile of the short circuit current when both the transistors are on at the same time. So here the NMOS is off. Here the PMOS is off. Here again the NMOS is off. So there is no short circuit current. But in these dashed regions, both the NMOS and the PMOS are on at the same time, and that's giving rise to the short circuit current. So let us come to some sort of rough model of the total energy dissipation because of the short circuit current. If I call it ESC, the short circuit, when the, let's say, so this transition is a discharging transition, right? You discharge output, and this is where you charge the output. So in the first case, when you are discharging the output, the ESC, when the V out goes from 1 to 0, you can say that the total energy dissipated here is going to be, what is the energy dissipation? So that's like integration of current multiplied by VDD, so ISC multiplied by VDD, right, over time. So T equals 0 to infinity. So if you just make a very crude assumption here that the VDD is of course constant, I'm just trying to find out the total area under this curve, right? And just assume that this looks like a rectangle. It goes up and then comes down, and it is a rectangle with a peak current, which is, let's call it I peak. So this is the peak short circuit current. And again, we can assume that during both these transitions, the peak doesn't change. So this is the peak short circuit current. And this is just a very crude model. This is not like an exact model. This is an approximate model, which works pretty well actually. So if you look at the total energy under this curve, the total energy associated with it, this will be this is happening over TR. So this is TR. So this is half I peak multiplied by VDD times TR, right? This is the total amount of energy dissipated during this short circuit event. Similarly, when I look at ESC, when the V out goes from 0 to 1, in this transition, this is TF. Again, this is like area under the curve, so I'm just looking at the total area under this triangle. So that will be half of I peak VDD TF, right? So this is the total energy dissipated during a 1 to 0 transition and a 0 to 1 transition. So the total short circuit energy during the full cycle will be half of I peak VDD TR plus TF, or in other words, I can call it I peak times VDD TR plus TF by 2. All right. So this is for a full cycle. So now we have two components of energy, dynamic energy. One is the switching component, and then the other one is this short circuit component. So we can say that the total energy dissipated during a full cycle. So let's call it dynamic energy. So this is the E-dyne, the total dynamic energy in a full cycle is CL VDD squared plus I peak times VDD times TR plus TF divided by 2. All right, so that's the total energy during a full cycle. And typically in processors, for well-designed processors, it is important that this, that rise times and the fall times are well maintained. If the rise times and the fall times are bad, so which means if the rise times and the fall times increase, the short circuit energy dissipation actually increases, and you end up with a bad design. So higher rise and fall times will translate to higher energy. That's why it is very important for us to maintain good slopes. So this is point 1. So it is important to maintain good signal slopes. If I do not do that, then the energy dissipation will be much higher. The second thing is for well-designed CMOS logic, and by well-designed I mean when the slopes are not bad, the slopes are a small portion of the total clock cycle, the short circuit energy or power, we'll look at power right after that, is about 10% to 20% of the total dynamic energy or power. All right, so that's important. So managing good signal transitions is important, and of course this is a very first order analysis. There are more there. If you want to exactly find out the short circuit portion of energy, you have to do spice simulations and do it numerically. But this gives you a good understanding of what's going on when you have a signal transition. All right. So we looked at the total dynamic energy. So now we go from energy to power. Energy to power. So what is the power dissipation, right? So that's what we care about. So how do we translate from energy to power? Before that, let me see if there are any questions. All right. So I don't see any questions. So if you have any questions, just let me know. All right. So how do you go from energy to power? Let's look at an inverter. The input of the inverter is making multiple switching events, like multiple times it is switching. Let's say the input is switching at frequency f. Right? So there's f is the frequency of switching, which means the number of 0 to 1 plus 1 to 0 transitions per second is f, right? That's what frequency is. If this is running at 1 gigahertz, then I can say that the total number of transitions, like complete transitions. When I say complete transitions, I mean 0 to 1 back from from 0 to 1 back from 1 to 0. So it's a full transition. So the total number of such full transitions is going to be f, right? That's what frequency means. Like a gigahertz will be 1 billion such events, right? So the energy per cycle is E dyne, right? So that's the total dynamic energy per cycle. Hence, the energy per second will be E dyne multiplied by the total number of cycles per second. So number of cycles per second, which is the same as f, right? That's the frequency. So E dyne multiplied by f. So that's the total energy per second, which is nothing other than power. So the power dissipated, the dynamic power dissipated is the product of the frequency of operation and the total, the dynamic energy dissipated per switching cycle. So the power dissipated. Now I'm going to write down what E dyne was. So E dyne was, the first component was CL VDD squared, and now I multiplied with F. So this is the dynamic, the switching dynamic power. And the next component is I peak VDD TR plus TF by 2 multiplied by F. So that's the short circuit power. So that's the total power dissipated by a processor, or not a processor, an inverter in this case, when it is going through f number of switching events per clock cycle. So you can see that the dependence is linear, right? If frequency increases, the power dissipation increases linearly. So frequency increase, if frequency increases, power dissipation increases as F. On the other hand, if VDD increases, you can see that the power dissipation increases as, and this is very, very important to understand, that the component here, the main component of energy anyways, is the switching component, right? And that's CV squared. So the power dissipation increases as VDD squared. So if I can reduce my power supply from, let's say, 1 volt to, let's say, 0.8 volt, it's not like a 20% decrease in power. The power, the power improvement will be like, it's like 36%. It's VDD squared, right? So there will be a significant gain if we can reduce the VDD of processors, of CMOS logic. And that's why, in the last 40 years, the power supply of processors have come down from, about 5 volts today down to about 0.8 volts. So today it's about 0.8 volts. It used to be about 5 volts, some 25 years back. And that scaling, that power supply voltage scaling over technology generations have resulted in lower power transistors and better power management techniques. Okay, so that is one of the main salient features of our designs today. So one of the things that you have to remember is if I have a processor, a relatively, let's say, large processor with many such gates and so on, right? And so on. So let's say I have a microprocessor with n gates. So one of the things that you can realize that if I have an inverter, let's say driving another inverter, if the input of the inverter switches, the output of the inverter will always switch. This will always switch. This will always switch. So if in a chain of inverters, if the input, the primary input toggles, if it switches, then every node of the inverter chain will also toggle, because the inverter does nothing other than just do a binary transition, right? 0 to 1 and 1 to 0. As opposed to that, imagine that you have this inverter, which is now not driving another inverter, but it is driving an AND gate, and maybe it is driving another inverter later on, right? And this one is constantly switching. If the input to the AND gate is a 1, then of course, this node is switching. If the input of the NAND gate is a 1, the output of the AND gate will also keep on switching all the time. This also switches all the time. So every node will keep on switching. However, if in the other condition where the input of the NAND gate is a 0, then the input switches, the output of the first inverter switches, but this AND gate output, I'm talking about an AND, so the AND gate output will always remain fixed to 0, and anything downstream, this inverter, output of this inverter, and whatever happens later on, they're all fixed at 0. So nothing 0 or 1, whatever the logic level might be. So there is no switching transition. So even if you have a large microprocessor with many logic gates, millions of logic gates, it does not mean that all the logic gates are switching all the time. Only a fraction of these logic gates are switching, depending on the logic, right? So if it's an AND gate, if one of the inputs is a 0, then the output does not switch. If it's an OR gate, if one of the inputs is a 1, then the output is also not switching, right? If instead of an AND gate, if it's, let's say, an OR, and let's say this is 1, then even if this is switching, this is fixed at 1, and this will be fixed at 0, and so on. So there is no switching. So since in our logic design there will be lots of AND gates and XOR gates and OR gates and so on, so not all the gates will be switching all the time. So what we can say is, let's say, the power in a processor with n gates, n logic gates, with m switching per cycle, which means I'm assuming that out of n, only m gates are switching in a particular clock cycle, and this m is just an estimate, right? This is like a statistical estimate. I'm just assuming that, let us assume out of a million logic gates, only 1,000 of them switch, right? Let's make that assumption. Then we can say that the total power dissipation, the P, is CL VDD squared F. But now instead of, and let me write down the other component as well, which is I peak VDD TR plus TF by 2 multiplied by F. But now instead of multiplying this with n, because there were n such gates in the processor, I have to multiply that with m. There are only m gates which are switching, and typically m is going to be much lower than n. So only a very small fraction of logic gates actually switch in a processor. So if I have to talk about so this is the total the power of the microprocessor. So here, if I now talk about the power per gate, right, per logic gate on an average, so this is like let's say the average power, right? So this is the average power per logic gate. Then we can say that this is CL VDD squared F plus I peak VDD TR plus TF by 2 multiplied by F M divided by N, right? So this is an important fraction. This is the fraction that tells me out of, let's say, 100 million gates that I have, how many of them are actually switching. And this is a very important component. So M over N represents number of gates actually switching divided by total number of gates. In other words, you can also say that it also represents the probability that a gate is switching. So this represents a probability. It represents a fraction. So if the probability is higher, it means that more and more gates are switching. If the probability is lower, it means less and less number of these gates are switching. So this M by N, I think I was using uppercase N, right? Yeah, uppercase N. So this was uppercase N. So M by N is called the switching activity. So there is no way to kind of exactly say what the switching activity is, because depending on what the workload is, what kind of programs you are executing, of course it is going to keep on changing. So it is like a statistical measure, and it is called alpha. So this is we use the symbol alpha for this. So it is a statistical measure, but it is but if you run a lot of workloads, a lot of programs, you can take some average value, and that is good enough. And in our power models that we use. So our power model eventually becomes, even for a gate, right? The alpha represents if I wait for a sufficiently longer period of time, for every gate I can say that alpha represents the probability that the output is switching. So the output of a gate is not switching every clock cycle, but it is switching with a probability of alpha. So the power is now going to be CL VDD squared alpha times F plus I have I pick, I have VDD, I'll have TR plus TF by 2 multiplied by alpha times F. So F becomes alpha F, because this represents the probability that there is an actual switching going on. In, let's say, a chain of inverters, alpha will be 1. It is always going to switch. But in an AND gate where one of the inputs is a 0, the alpha will be 0, right? So there is no switching at the output. So on an aggregate, we can find out an approximate value of alpha, which satisfies all the gates in the processor. And in today's microprocessors, alpha is approximately between 5% to 10%. So it's actually very, very low. And because there are so many things going on, and there are so many complex logic going on, that there is actually the value of switching activity is, the probability is pretty low, and that's what keeps the power dissipation in a processor under control. Like if everything were switching all the time, you can do some very rough estimates, and you can very easily show that the total power density, like the microprocessor is very small, and if everything were switching all the time, all gates, typically today in a large microprocessor, I will have about 10 billion transistors, so about a couple of billion gates, billion with a B, right? And if all of them were switching every clock cycle, and the clock cycles are 1 gigahertz, right? So it's running at about a gigahertz of a clock frequency. If everybody were switching all the time, then the total power density will be so large that the temperature of this will be, I think there were some interesting plots from Intel at some point where they showed that the temperature of that would be very close to that of a nozzle of a rocket. So a rocket nozzle will have, the temperature of a microprocessor will be at the same level as the temperature of a rocket nozzle. And the only reason it is not that is because of this alpha. Because the logic is such that it reduces the switching activity or the probability of switching to a level which is 5% or 10% of the maximum, and that keeps the power levels to like 100 watts, or large processors will be about 100 watts, or even like 40 watts. Laptops are in the order of 10 watts. Mobile phones are in the order of 1 watt, couple of watts. So that's kind of the the level of power dissipation that we tolerate these days. So if you look at so this is the total discussion on the dynamic component of power. As I said, the leakage component, there is another part which is the static portion of the power dissipation. I'm trying to go back to my first slide. So we talked about the switching power, we talked about the short circuit power, we talked about both of these, and that gave rise to the total dynamic power, equation of total dynamic power. Apart from the dynamic power, there is also what is called the static power, and this is something that you guys have not discussed much in 3150. I'm sure you have not looked at leakage power in details, but you know that when we talk about transistors being off, right? So when we talk about transistors, we say that if this is the VGS, this is ground, and this is whatever VDS. When you draw VGS versus IDS, we say that below the threshold voltage of the transistor there is almost zero current, and then the current increases quadratically, right? So our assumption is that below the threshold voltage of the transistor there is actually no current. This is a good approximation for for the first VLSI course that you would take, but later on you will see that that's not a good approximation anymore, because today in microprocessors we have, along with all this dynamic energy and all, we have what is called static power. So there is always some sort of like power that is drawn from VDD directly to ground, even if the transistor is off. So even if the PMOS is off, let's say this is 1, right? The PMOS is off, there is some power, there is some current that flows from VDD to ground. Even if it is 0 and this is off, even then there is some off current that will flow from VDD to ground. So this is called the leakage current or static current that always flows through the transistor even when it is not switching. Okay, so this gives rise to static power. So we are discussing static power. So this is so realize that this is not energy. This is power, because energy is associated with an activity. So you need so much energy to do something. You need kilojoules of energy to climb a mountain. So for a particular activity you can associate energy. If current is constantly flowing from a supply, then there is no notion of energy, right? The longer you wait, the more energy that you spend. So the notion is now that of power, because you are drawing constant current from the supply. So when we talk about leakage, we are not accustomed to talking about energy. We are thinking about power, right? So we are talking about the total leakage power, the total static current that is drawn from the supply that gives rise to the static power dissipation. So on an average, right? Let's say let's say I off of the NMOS is, let's say, the off current of the NMOS. So we call it the off current, which is the leakage current. And similarly, let's say I off of the PMOS is the off current of the PMOS. Then we can say that the total leakage or static power is going to be, again, simply current multiplied by voltage. So it's VDD multiplied by I off of the NMOS plus I off of the PMOS divided by 2. So what did I do? I said that this essentially assumes that half the time NMOS is leaking, which means V in is 0, and half the time PMOS is leaking, where V in is 1, right? So with that assumption, again a very crude assumption, we are assuming that in a logic gate, half the time the NMOS, the pull-up network, is leaking, and the rest of the time the pull-down network is leaking. So I can assume that the total leakage power is it has this kind of a formula, which is like half of it is NMOS, half of it is PMOS, and then multiply that with VDD. So the total power dissipated. Now if you look at the total average power, the total P average that is dissipated will become the total, which is let's call it CL VDD squared times alpha times F, right? So this is the switching power. Plus, we have CL VDD times I peak. Oh, sorry, there is no CL. Sorry. I peak VDD TR plus TF by 2 times alpha times F. Both of these are related to frequency because they are related to switching. So this is the short circuit. All of them together form the total dynamic power, and they are related to switching. So if if F is 0 when there is no switching, the dynamic component of power is 0. So this is completely related to switching. So if you stop switching, then it just leaks. Plus, I have something which is the total, let's call it this way. So this is VDD I of n plus I of p divided by 2. So this is the static power. Let's call it leakage power first. Leakage power. This is the static component power. Static power. And this you cannot avoid this even if there is no switching, it'll always be there. That's why, and this is the reason why, let's say you have your cell phone and you keep your cell phone, even if you're not using your cell phone, if you leave it for like a few days, eventually you will see that the battery has drained out. I mean, if you are not doing anything, why is the battery leaking out? And this is exactly the reason why the battery would leak out. Because even if you're not doing anything, there is this very thin flow of current, right? This like tickling of current that's going on, and this trickle discharge will essentially keep on discharging this battery that you have on your cell phone, and it will eventually leak out, and you won't have any power or any energy left in the system. So one of the things, one of the main takeaways from this is, the dependencies. So the dynamic power increases as VDD squared, right? Because of the switching part. That's the strong dependence. The static portion, at least to the first order, depends on VDD, right? Assuming that the off currents remain constant, it is more or less dependent on VDD. This is the static portion. And you can also see that when we looked at delays, for example, the switching delay and all, you saw that the switching, one of the popular models of the switching delay will essentially tell you that the switching delay is about 1 over VDD, right? So that's the thing. So a linear increase in VDD will give you a linear increase in frequency. So this means that the reciprocal of delay is frequency. So frequency is approximately proportional to VDD, right? So what we can say is 2x increase in VDD can make logic 2x faster but burn 4x higher power. So this is important to know, that the penalty that you pay in making things faster is quadratic. It's not linear. So if you want to improve performance by 10%, you will pay a lot in terms of the energy dissipation. Or in the other way around, if you want to reduce your energy dissipation, if you lower your supply voltage, you can get a lot more bang for the buck. Like if you lower the supply voltage, you will have significantly lower power dissipation as well. As a result, in today's processors, for example, you will learn about these things in more advanced courses, and maybe even not in your undergraduates, a little bit in 4130 if you guys take 4130, but most of this if you go to grad school, you will learn more about these things. But the whole idea is, if you look at today's your cell phone, for example, when you are playing a video game on your cell phone, it's doing a lot of things. It's cranking up the speed, and it's graphics are intensive. So what ends up happening is it's running at what is called the full VDD, the maximum throttle, and you are going to dissipate a lot of energy. The whole thing becomes very, very hot. The frequency is high, the voltage is high, so that's like the full steam. On the other hand, let's say if you're using your cell phone and you're only using it for surfing the internet or doing something where you don't need a lot of computation, then the processor inside your cell phone is smart enough that it will reduce its power supply and it will meet the frequency requirement that will just sustain that particular workload, which means it will sustain the amount of activity that you need to do that web surfing that you're doing. But in the process of reducing the VDD, it will actually save power quadratically, and the whole thing will be way more power efficient. So today's processors do not run at a fixed frequency and voltage. It keeps on changing the frequency and the voltage depending on what you are working on. So if it's whether it's computationally intensive or not, and if it is intensive, it will crank up the supply, it will burn more power. But if you're not doing something, in most cases we don't do anything which requires a lot of compute. We are checking emails, we are let's say surfing the web or listening to music. Doesn't require a lot of computation. In that case, it's going to lower the supply voltage so that it can still, depending on this dependency, it can still maintain enough frequency, but realize that the total component of power dissipation will be significantly lower. The other thing to remember is, out of these three components of power dissipation, as I said, during, dynamic power, this will be, I'd say, this is about, 10% to 20% of the total dynamic power. So this will be about 80% to 90% of the total dynamic power. And the leakage, is, it depends on the frequency, right? So the portion of leakage versus dynamic, this is not very easy to understand. It depends on the frequency and what you're doing. So if you're doing a lot of activity, then of course you're dominated by leakage power. If there is not enough activity, if your phone is on standby, or your computer, your laptop on your desk is just connected to the outlet and you're not doing anything, then it is just burning static power. So depending on the activity and the workload, the ratio between dynamic power and static power will keep on changing. But today, in today's technology, the static portion of power is significant enough that we have to seriously worry about it, and we have to do all kinds of circuit techniques to be able to reduce that static power. It is not negligible. So although in the treatment of this course so far you have seen that static power is like off current is negligible, we have never discussed the off current scenarios, but realize that this is not negligible when you are leaking off current for a long period of time, right? When for days, let's say, you will leak it out, then there is enough off current to leak out the entire battery of your cell phone or your iPad. All right, so that's all that I have for this module. So this is an introduction to all the different components of power dissipation and energy dissipation, and should be enough for you guys in this course. And later on, you can look at more complex, complex analysis of these same items when you take advanced courses. But this gives you a good understanding of the basics of power dissipation in CMOS.